by the reviewer, and the response to the reviewers, and the response to the response of reviewers are all very exciting. Actually, it's quite interesting to read what the people have been debating about, and it's really a great work. So with that, I will give the rest up to Patrick. And normally we run about 40-45 minutes and leave another 10-15 minutes for interaction with our participants. So with that, Patrick.
Thank you very much. And thanks for having me. I'll try and talk slowly because I know lots of you, English won't be the first language. But if you need me to clarify anything that I'm saying, please interrupt me and let me know, and I'll re-explain things as we go along. So the first I'm going to start with a motivation for the talk. So why we decided to conduct this research. And what we wanted to know was how to track dynamic topography through time. So dynamic topography is topography of the Earth's surface generated by mantle convective processes. So when you have low density hot material upwelling in the mantle, it produces uplift at the surface, and where cold dense stuff descends in the mantle, it causes subsidence at Earth's surface. These dynamic topographic events can occur over amplitudes of up to 1 kilometer, over thousands of kilometers in wavelength, and can vary over thousands to millions of years. The problem is that they're often masked by tectonic processes such as mountain building or rifting. And once the mantle convective cell dies away, the topography dies away. And so although we have good observations for the present day, it's difficult to see how this has changed in the past. So I'm going to start with our present day observations. The first is residual depth anomalies. So the way these work is in the oceans, we know how seafloor height changes with the age of the seafloor. So as the oceans grow away from the ridge, they subside at a predictable rate, and we can measure the difference between the observed seafloor depth and what we predict from the model, and we say that these changes are due to dynamic topography. Unfortunately, these only work for the oceans. The second data set we use at the present day is long wavelength gravity. So traditional tectonic topography is supported by a crustal root or by thinning of the crust if it's subsiding. And they won't have a large gravity anomaly associated with them. But if topography is supported by the mantle, instead, you'll have positive gravity anomalies, so red colors above upwelling zones and uplift zones, and blue around downwelling zones. So you can see areas such as the Colorado Plateau is in red and the Congo Basin is in blue. The final observation at the present day is using seismic tomography. So shear waves travel through Earth's mantle, and their speed is a function of temperature. So in areas where you have high temperatures, you have slower shear wave velocities, so red on this map. And where you have fast velocities in the mantle, you have colder mantle, and that's blue on this map. As I said, the problem is that these are only snapshots for the present day. So if we want to go back in time, the traditional observations are things like uplifted marine sediments, changes to how erosion occurs, raised or submerged beaches or atolls, and changes to sedimentation in sedimentary basins. The problem is that all of these different observations can also be generated by tectonic topography. They also deteriorate in quality the further back in time you go. So what we thought was maybe intraplate volcanism could be a really useful additional observation, because intraplate volcanism is generally generated one of two ways. Either you increase the temperature of the upper mantle, and that deepens the solidus and generates melting, or you can thin the lithosphere, and that also allows melting to occur as the lithosphere becomes thinner than the solidus. Both of these processes, increasing the temperature of the mantle and decreasing lithospheric thickness generate uplift. And so when you have intraplate volcanism, you also have dynamic uplift. And so we're wanting to test this idea. So our motivation questions for this talk are: what can intraplate magmatism tell geologists about mantle temperatures? And then can we use that magmatism in the rock record as a proxy for dynamic topography back in time? Here's an outline of what I'm going to be talking about. First, I'm going to introduce the intraplate magmatic database we were talking about at the start. I'm then going to compare spatial and geochemical correlations between this database and seismic tomography models. I'm then going to use both seismic tomographic and geochemical techniques to estimate mantle potential temperature, and then show you a case study for North Africa. Finally, I'm going to describe some more recent work I've been doing looking at geodynamic modeling and including melting within geodynamic models. So here is my database that I generated during my PhD. It's mainly basaltic or mafic samples, dated between 23 million years ago and the present day. So the start of the Neogene to the present day. But in this talk, I'm just going to be concentrating on the last 10 million years or so, which is roughly 20,000 samples, just shown in yellow here. We're going to compare that database to tomography, and specifically, we're going to compare it to the Schaefer and Lebedev 2013 seismic shear wave model at 150 plus or minus 25 kilometers depth. As I hope you'll agree, most of the yellow dots appear on areas that are red in the map, or hot temperatures at 150 kilometers depth. We can compare that with some zoom in so you can see this a little better. On the left-hand side, this is the Schaefer and Lebedev model. And on the right-hand side, I'm showing some high-resolution local seismic tomography models, which maybe do a better job of picking out the finer features in each area. So you can see Iceland, the Canary Islands, southern Spain, the Massif Central, Eifel, Pannonian Basin, Western Turkey. In both models are underlain by slow velocities at the present day, or hot temperatures. The same is true in America. We see the Colorado Plateau and the Snake River Plain areas picked out nicely by low velocity anomalies in both models. As I hope you'll agree, the more modern or higher resolution models do a better job of fitting the data. And I think this shows that as tomography models improve, I think the correlations that I show in this talk between intraplate volcanism and seismic tomography will also improve. Again, the same is true for Australia and for Antarctica. So the Sydney and Mount Erebus regions are underlain by slow velocities at the present day. So that's a qualitative look at the relationship between the two. We can also look at that quantitatively using cumulative global area distributions. So the idea here is we subdivide the world into 1 degree latitude by 1 degree longitude grid squares. And we look at the velocity anomaly in each grid square, and those grids are weighted by the cosine of latitude. This is because grid squares close to the poles are smaller than grid squares at the equator. In black, we have the cumulative distribution of shear wave velocities in our tomography model. And in red, we have only those grid squares that have intraplate volcanism in them. As you can see, it's shifted to the left, and we find that while around 60% of Earth's surface is underlain by slow velocity anomalies, this increases to over 90% when we only look at areas with intraplate volcanism. This association between intraplate volcanism and slow shear wave velocities is very difficult to, it would be almost impossible for this to be a random association using a Kolmogorov-Smirnov test. And the same is true for a wide range of different tomography models. We can then take our tomography model and convert it into lithospheric thickness using the shear wave velocity to temperature conversion of Hogarth et al. 2020. And when we compare our volcanic database to this model, I hope you'll agree that the vast majority of samples occur on thin lithosphere, so lithosphere less than 100 kilometers thick. Again, we can look at this quantitatively, and we find that while around 60% of the Earth's surface is less than 100 kilometers thick, over 95% of intraplate volcanic samples occur on lithosphere less than 100 kilometers thick. Intraplate volcanism also coincides with residual depth anomalies and with positive gravity anomalies, which were the two other observations we discussed at the start for dynamic topography. So I hope you'll agree that if you find an intraplate volcanic rock in the rock record in your stratigraphy, you can say with a degree of confidence that it probably occurred on thin lithosphere, underlain by anomalously hot mantle. So that area was probably dynamically up or uplifted by the mantle, but what we really want to know is by how much. And so to be able to know that, we need to be able to generate correlations between geochemistry, which we can take from the rock, and tomography for the present day. So then we can use the geochemistry of our intraplate volcanic rocks in the past to estimate dynamic topography or mantle temperature. So to do that, I take my original database and I filter it to only have the samples that closely reflect mantle melting at the present day. So I only use samples less than 10 million years old that have moved less than 400 kilometers from when they initially erupted. I then only take samples with high magnesium contents in order to reduce the effects of fractional crystallization. And then again, I take that database and divide it into 1 degree latitude by 1 degree longitude grid squares. Again, each grid square is weighted by the cosine of latitude when we're looking at correlations. Finally, I only include grid squares that have more than 5 samples in order to reduce the effects of sampling error. And then again, we're comparing to our tomographic models at 150 kilometers depth, plus or minus 25 kilometers. What we're going to compare to seismic tomography is lanthanum over samarium. Lanthanum and samarium are both incompatible elements, but lanthanum is more incompatible than samarium during mantle melting. And so as melt fraction increases, lanthanum over samarium reduces. If we say that melt fraction is a function of mantle temperature, then we can say that lanthanum over samarium is a rough proxy for temperature. Now, there are many problems with using such a simple proxy. Changes in lithospheric thickness rather than temperature could change melt fraction. Your source composition might vary, and that would vary your lanthanum over samarium ratio. And then there's a whole host of different things that can happen between the mantle and the surface that can change your lanthanum over samarium ratio. The same is true for saying that shear wave velocities are directly affected by temperature and directly show the temperature structure of the mantle. But our hope is that if we take a global view of these two data sets, these errors will become noise and we'll be able to see a clear correlation between these two data sets. And if we do, I believe that's a very powerful signal, considering that these two data sets are subject to completely different forms of error. And this is our global correlation for the Shear and Lebedev 2013 model. As you can see, in areas with slower velocity anomalies or hotter temperatures, we get lower lanthanum over samarium ratios or higher melt fractions, which is what we were expecting to see. We can then compute a correlation coefficient between these data, and we get a correlation coefficient of 0.65. And that correlation coefficient does not change significantly if we change how we bin or filter the data. Now, I would say as a word of warning that there's no reason why these two observations should linearly correlate, but we're using a simple linear case for now, and we'll change that as we go on through the talk. And we get a similar correlation with a wide range of different tomography models. My intraplate database is not strictly intraplate. There are areas such as Iceland, which sit on mid-ocean ridges, and areas such as Mexico, which are above subduction zones. But I chose data that is intraplate-like, so areas of subduction or where slab rollback has allowed intraplate processes to occur. However, if we remove those areas on rifts or near subduction zones, we still get a good correlation between these two sets of observations. Although our correlation doesn't change significantly if we change the way we filter the data, it changes significantly as a function of depth. So we find our highest correlation coefficient at around 125 kilometers depth, and this correlation decreases as we become shallower because crustal bleeding or changes in lithospheric thickness begin to affect the correlation. And as we go deeper, our correlation reduces because the temperature structure the tomography is seeing is different to that in the melt region. And again, this is true for a wide range of tomography models. Now, although I said that our correlation between shear wave velocity and lanthanum over samarium was because of temperature variations, it could conceivably be due to lithospheric thickness variations, because thicker lithosphere causes colder shear wave, thicker lithosphere means that you could have faster shear wave velocities at deeper depths, and a thicker lithospheric lid can limit melting, and so you have a higher lanthanum over samarium ratio. So our correlation could be due to lithospheric thickness variations. It could also be due to variations in mantle composition, because mantle composition also affects shear wave velocities and lanthanum over samarium ratios. So we need to test whether these two factors are affecting our correlation. So first, we start with our tomography models, and we find that if we compare a correlation between lithospheric thickness and shear wave velocity between our tomographic model and the lithospheric thickness grid generated from that model, which we are using during this study, we find that the correlation between the two becomes negligible at 150 kilometers depth. So you get a very strong correlation between the two at shallow depths, and this correlation becomes negligible at the depths at which we are looking at. This means that we do not think that lithospheric thickness variations are controlling shear wave velocity variations at 150 kilometers depth. So when we look at shear wave velocities at that depth, we're looking at temperature variations in the asthenospheric mantle. And that's the same for a wide range of tomography models. Next, we want to see if lithospheric thickness variations or compositional variations affect our lanthanum over samarium ratios. And to do that, we're going to use principal component analysis. So I'm just going to quickly explain what principal component analysis is. Essentially, it's a way of reorientating the axes that you look at data from. So in this case, we have two variables, X and Y, and we're going to tilt the axes to look at, instead of X and Y, principal components 1 and 2. Principal component 1 is always the line of best fit through the data. And the way we describe each principal component is in terms of variance and weighting. So the variance is how much of the data does this principal component describe. So in this case, it's around 80% or 85% of the variance in the data. And the weighting is essentially the gradient of the line. So in this case, both X and Y have a positive weighting and they're equal. This means that if you move once in X, you move once in Y, and that describes the gradient of the line. All principal components are orthogonal to each other or at 90 degrees to each other. And so principal component 2 is 90 degrees to principal component 1. It describes the rest of the variance in the data set, and its weighting is negative in X and positive in Y. That means that a move of -1 in X is matched by a move of 1 in y, and that describes the gradient of principal component 2. In this case, we're going to have 8 components, and they've been carefully chosen so that we can look at different processes within the mantle. So we use barium and potassium are fluid mobile, and so if you have subduction or metasomatism, these will be increased, whereas if you have subduction, niobium is decreased because it's retained within rutile in the subducting slab. So if subduction and metasomatism are key factors, we will have high barium, potassium, low niobium. Then we have a series of elements that are strongly affected, principally affected by melt fraction, including lanthanum and samarium. And then finally, we include ytterbium, which is sensitive to whether garnet is present within the mantle. So this is most sensitive to the depth at which melting occurs. Our first principal component is roughly 80% of the data, and it's almost horizontal or equal for all components except for ytterbium, which is almost 0. This is our melt fraction signal. So it should correlate very nicely with lanthanum over samarium. Next, we have principal component 2, which is roughly 15% of the data set. And this one is almost 0 for everything except for niobium, except for ytterbium, where it's very high weighting. So this is our depth of melting signal. And then finally, roughly 7% of the variance can be described by principal component 3, which is positive for barium, potassium, negative for niobium. So this is our subduction or metasomatism signal. So you can see that our geochemical data is dominated by a melt fraction signal with a minor depth of melting and metasomatism or subduction signals. We can see that by comparing each principal component to lanthanum over samarium and shear wave velocity. So here we have principal components 1, 2, and 3. And you can see there's a very strong correlation between lanthanum over samarium and principal component 1, and a good correlation between shear wave velocity and principal component 1, and a very poor correlation between these two variables and principal component 2 and principal component 3. So we think that this shows that both lanthanum over samarium and shear wave velocity are sensitive to temperature variations, with lanthanum over samarium being sensitive to melt fraction rather than depth of melting. Now, although we believe that our trace element concentrations and shear wave velocities are affected dominantly by temperature variations, we need to be able to directly compare these two observations within the same framework. So to do that, we're going to take our trace element data and our shear wave velocities and convert both into temperature. So to change shear wave velocity into temperature, we're using the parameterization of Hoggard et al. 2020, and that's based on the anelasticity equations of Yamauchi and Takai 2016. So the way these work is that at low temperatures, so temperatures on the x-axis here, at low temperatures rocks behave elastically, and so there's roughly a linear relationship between shear wave velocity and temperature. As you approach the solidus, anelastic effects take over and you see a sharp decrease in shear wave velocity as a function of temperature. And then once you reach the solidus, if you assume that melt is instantaneously extracted, you go back to an elastic relationship. These curves can be described by equations, and those equations have 7 free parameters or variables that need to be defined. The way Hoggard et al. 2020 defined them is by reducing the misfit between the temperature models generated by these curves and 4 different observations or models. So these are, you have to fit the plate cooling relationship in the oceans. You have to have an average temperature in the mantle of, an average potential temperature in the mantle of 1334 degrees C. And you have to have a reasonable attenuation and viscosity for your mantle as well. So that by doing this conversion, we go from having a lanthanum over samarium to shear wave velocity relationship to a lanthanum over samarium versus tomographic temperature relationship. And you can see we still have a nice linear relationship between the two. Now we want to convert lanthanum over samarium or trace element chemistry into temperature. And the way we do that is by using the rare earth elements. So they're plotted down the bottom here, and it's concentration on the y-axis. So as temperatures increase, which are shown here, our melt fraction increases and our rare earth element concentrations reduce. This is because rare earth elements are incompatible during melting. However, the rare earth elements, the right-hand side of the graph, so these ones here, are also sensitive to depth of melting and to whether garnet or spinel is present within the mantle. So you can see this here, as lithospheric thickness increases and we reduce the amount of melting in the spinel region versus the amount of melting in the garnet region, our line increases in gradient. So melt fraction raises or lowers the line, and whether you have spinel or garnet melting present changes the gradient of the line. We calculated a rare earth element curve for every lithospheric thickness mantle temperature combination, and then we use that database to find the best fitting rare earth element curve to observe data. So you can see this here for Hawaii. So this is one of our intraplate average grid squares, rare earth element concentrations. And that's best fit by the red line here, which is generated using a lithospheric thickness of roughly 50 kilometers and a mantle temperature of roughly 1400 degrees C. We then assign an error to this estimate by finding the models that fit within 1.5 times the minimum misfit of the model. It should be emphasized that this is purely a model misfit and not a general misfit. So we're not propagating errors through the model. This is purely a model misfit. The misfit on temperature in general would be much larger. Instead of looking at this in depth melt fraction space, we can look at it in terms of misfit. And so here you can see we get a nice global misfit well that again is around 50 kilometers depth, 1400 degrees temperature. If we change to the Western Transition Zone, which is another area of the US, you can see that the rare earth element profile increases in gradient, and therefore we're fit with thicker lithosphere and lower temperatures. When we do that for all of our data set, this is the correlation we get between geochemical temperature and tomographic temperature. So although the two vary by roughly 100 degrees in some places, we get a reasonable correlation between the two. I can show this spatially. So here's our map of tomographic and geochemical temperatures. And I'm going to show you a cross section going through Europe and Arabia and Africa. So here we start in Iceland, and then we go through the North Sea, the Eifel region of France, Germany, sorry, Turkey, Arabia, Afar, and Tanzania. And you can see lanthanum over samarium is shown by these dots. So it starts with very low lanthanum over samarium, then there's no melting, and then we see lanthanum over samarium decreases and then increases as we go through Europe and Asia and then down through Africa. And that's matched quite nicely by our shear wave velocity model, which is shown by this red line. So it goes, it's lowest here, increases, decreases, and then increases again. When we convert both to temperature, these are the estimates we get. And again, we get a reasonable agreement between the two. And again, our lithospheric thickness estimates also agree nicely. Now, these blue areas here indicate areas of Cenozoic marine limestones, which are underformed and are now sitting at elevations of 1 to 2 kilometers. In order to generate this amount of uplift, it could occur one of two ways. Either you need a temperature anomaly of up to 200 degrees C, or you need to remove around 50 to 100 kilometers of lithosphere. those are the two extreme end members, and it's probably somewhere between the two. There are many areas like Turkey and Arabia where we see intraplate volcanism at the present day occurring at the same time as a large amount of uplift. And I want to show you an example where I think using these intraplate volcanic observations could allow you to understand a little better the system within which you are working. And so I'm going to show you an example from earlier in my PhD from North Africa. So there's a large amount of volcanism in this area of Africa, and most of that volcanism has occurred within the last 10 million years. The volcanism itself is quite poorly studied, but it occurs adjacent to the Sirte Basin, which is one of the largest oil reserves on the planet. If I show you a cross-section within the basin, you'll see that there's a large erosional unconformity on the western side of the basin. So the whole basin has been tilted at some point in the last 20 million years. It's very important to know when this occurred, because the shales in the upper Cretaceous, which generate the oil, have a very specific oil window. And so we need to know when they were uplifted due to erosion and left that window. And it also when you tilt sediments like this, you change the traps within the basin and cause oil to migrate westwards. So it's very important to know when this occurred. Now, there's two main hypotheses for why the Sirte Basin uplifted and tilted. One is that there were changes to the Italian subduction zone, which caused far field stresses on the African plate. And the other one is the same, but with the Arabian subduction zone. I hope you'll agree as part of this talk that instead it's maybe this area has been uplifted due to the same processes that generated the volcanism 10 million years ago. So we can take our geochemical data and our tomography model, and you can see there's a slow shear wave velocity in the mantle beneath the Sirte Basin, and our Lanthanum over Samarium value is on the lower end. So we're expecting large amounts of melting within this area of North Africa. So I hope you'll agree that this observation is key for understanding when the Sirte Basin began being uplifted. It was probably at the same time as volcanism began in Libya. That is a published work of mine, and now I'm going to very quickly show you some geodynamic modeling that I've been doing, that I did when I was in Australia working at ANU. So I hope you'll agree, throughout this talk I've shown that intraplate volcanism can tell us quite a lot of information about the temperature structure of the mantle. And this is very interesting, I think, for geodynamic modelers, because generally when you generate a geodynamic model, you can only compare to present day observations. So for example, if you use tomography to generate your model, you can then compare to things like gravity anomalies at the present day or dynamic topography at the present day. But if you were to make a geodynamic model of the past, say you wanted to make a geodynamic model of the Siberian traps, you would have very little data to compare the output of your model to. So our idea is that if you can generate melting and melt composition within your geodynamic model, you could then compare that to intraplate volcanic data in order to understand whether your model is doing a good job or not. So obviously we're not going to begin with something as complicated as the Siberian traps. Instead, we're looking at mid-ocean ridges. So we have impose a spreading rate at the surface and set a temperature in the mantle. And within our model, we generate a melting wedge, and we calculate the crustal thickness generated at the surface and melt composition. To do that, we track the flow of particles within our model. And each particle we track pressure, temperature, melt fraction, and chemistry. And these flow through the model. So you can see this here. Over time, these particles cross the solidus and generate melting, and then they spread away as the plates pull apart. And we end up with a nice melting region, and we have, we know the melt distribution within our triangle. In order to parameterize the mineralogy in the system, we use a series of different mineralogical experiments from the 90s or from the 1990s, and then we fit these using simple parameterizations as a function of both pressure, which is shown up here, and melt fraction, which is shown along the x-axis. So each of these is modal mineralogy as a function of melt fraction at different pressures. So you can see olivine, clinoperoxene, orthoperoxene, garnet, etc. And you can see our model fits the data reasonably well. We then also have, we also parameterize our partition coefficients for each element based on different parameterizations that vary as a function of melt chemistry, melt fraction, and pressure and temperature. And the majority of these are from Sun and Liang or Yao 2012. So just to show you one of these model results, this is for a single particle just traveling vertically. You can see as we cross the solidus, melt fraction begins to increase, which is shown by X. Temperature begins to decrease, and our mineralogy, clinoperoxene decreases rapidly, and olivine and orthoperoxene begin to increase. Once clinoperoxene is exhausted, olivine begins to decrease, and orthoperoxene begins to increase again. This leads to interesting relationships between melt fraction, temperature, and sodium concentrations. This is because deep within the mantle, the sodium is retained within jadeite. And as the amount of jadeite decreases, sodium becomes more incompatible. And so you end up with high concentrations of sodium. And then sodium begins to be exhausted within the mantle. And so the amount of sodium that you have within your melt slowly decreases after that. Lanthanum is always incompatible during melting. So it begins very highly concentrated in the melt, and then that concentration slowly reduces over time. At the spinel garnet transition zone, there's a small change in the concentration of lanthanum as we get a radical change in the partition coefficients at that boundary. So we can now compare, we can then take our mid-ocean ridge melting model and convert that into estimates of sodium concentration. And on the right-hand side here, I'm showing gadolinium plus samarium over titanium, which is a commonly used proxy for melt fraction within mid-ocean ridges. As we increase temperature within our model, our mid-ocean ridge melting region increases in size. And as we increase our spreading rate, again, our mid-ocean ridge melting region increases in size. And this has a strong effect on the chemistry that we see at the mid-ocean, at the ridge axis. So you can see, so to do that, we're going to compare to observational data. So we take crustal thickness estimates from Hoggard et al. 2017 and temperature estimates at mid-ocean ridges from Richards et al. 2020. We then use spreading rates from Argus et al. 2011 and sodium concentrations from Gale et al. 2014. So first, if I show you our models, we do a good job of fitting sodium concentrations and samarium plus gadolinium over titanium concentrations as a function of potential temperature and of spreading rate. but we do a poor job of fitting crustal thickness observations. This is because our model assumes that all crust is instantaneously extracted and no melt is left behind in the mantle. We can vary what's called the critical distance and assume that some melt is left behind within the mantle. And this allows us to fit crustal thickness data nicely with not very much difference in our sodium and samarium plus gadolinium over titanium concentrations. Although I use this model at mid-ocean ridges, it works in a variety of different settings, including at lithospheric steps. So here's a model where we have a step in lithospheric thickness, and as the model propagates through time, so we start at 0 MA, we go to 20 MA, you can see that we generate a large convective cell at the lithospheric step, and our melt fraction starts high and decreases through time as the lithosphere above re-thickens. This change in melt fraction is also seen in our estimates of melt chemistry. So you can see lanthanum over samarium increases through time, and samarium over ytterbium also increases through time within the model. So just some overall conclusions from my talk. I compiled this global intraplate volcanic database, which is now publicly available. Please use it if you want to. And then I used that database to look at correlations between the spatial and chemical distribution within the database versus shear wave velocities and lithospheric thickness. And then estimated mantle temperatures using both geochemical and tomographic techniques. I think this work shows that intraplate magmatism is a useful indicator of mantle conditions, particularly it tells you when the lithosphere is thin, and lanthanum over samarium can be used as a rough proxy for mantle temperature. And I'm beginning to incorporate these observations into geochemical and geodynamic modeling. If you want to know any more about this work, here are some QR codes to 2 papers. One, the Nature Communications paper that was mentioned earlier, and the other one, my paper looking at North Africa. And then the geodynamic modeling is currently in review at G-Cubed, but you can see a preprint if you're interested. Thank you very much.
Thank you very much, Patrick. Now it's time for us to ask questions. So if you have questions, feel free to open your mic, or you could leave your question in the chat and I could read the questions on your behalf. So please go ahead.
Hi, Patrick. Very fascinating work. So I really enjoy the talk. I'm a seismologist, so I don't know too much about geochemistry. So my question may be naive. I'm just wondering, since you show the maximum correlation coefficient at 150 kilometer depth, so I'm just wondering, so for geochemistry data, do you actually have the depth sensitivity? Like you can constrain the depth of the source region of the volcanic?
So the melt region is probably shallower than that. But obviously, when you have melt within the mantle, that can strongly affect shear wave velocities. And so I think the correlation is best at 150 kilometers depth, because as you go shallower than that, you start to have melting effects that also play a role in changing your shear wave velocities. And we're trying to avoid that by looking at a depth below the solidus. So I agree that the melt region isn't that deep, and so we're maybe not we're maybe not sensitive to temperatures at 150 kilometers depth, but the resolution of these global models is normally around plus or minus 50 kilometers in depth. And so I think we're probably seeing similar temperature structure in those 2 places, but we're trying to avoid including either the lithosphere above in that 50 kilometers or the effect of melting within the shear wave velocities.
Okay, I see. Thanks.
Next question, please.
Hi, Patrick. Can you hear me? Hello?
Hello? Yeah, I can hear you.
Okay. So network. I have a small question. You mentioned that for your volcanoes, over 90% occur in regions with a lithosphere less than 100 kilometers. I wonder if you have checked the samples that lie beneath 100 kilometers. That is, the lithospheric thickness is larger than 100 kilometers. So is there any special features about this? Maybe it's because the tomography resolution, or maybe special tectonic regions. Thank you.
Yeah, I think it's exactly as you say. It's because those regions occur right next to craton edges, and so often they are not. So because of that, I think the resolution of the tomography models isn't good enough. So there's areas such as here, right on the edge of the West African craton. That's one area that's above 100 kilometers thick. But I think if you were to look at local observations, you wouldn't have it 100 kilometers thick. It would be thinner than that. The same with just the very edge of this area here. Is that in China, or is it in Cambodia? Or I think that is China, isn't it? There.
I guess it's in China, in Tibet.
Yeah. Again, that area is plotting on top of the thicker craton, but it's probably on the thinner shelf. And again, it's just the resolution of the tomography is not good enough.
Okay, so it's because mainly because the resolutions. Okay, thank you.
Yeah, there are some areas such as here in Runway, where people think that the melting is generated entirely within the lithosphere and is very, very small melt fraction and with a very high water content. So there are some regions where you would expect melting to occur in or beneath lithosphere that's very thick, but you would expect extremely small melt fractions in those places.
Okay, thanks.
Okay, thank you for the question. I think Yang is from Southern University of Science and Technology of China in geodynamics. The first question was from Yunfeng Chen from Zhejiang University in seismology. So the third question is in the chat. That's Chuntao Liu from Zhejiang University, a geochemist, and is asking about the topography, but it's a more like wider question about the Earth's early crossing in the Archean. So what do you think of the mechanism of driving the change of topography at the Earth's surface? Is it related to change of dynamic topography of a lithospheric mantle? As you discussed in your talk, it's possible to model the dynamic topography of the mantle in the late Archean, when the Earth was likely very much covered by water.
Oh, I don't know. I think it's very difficult. I'm currently looking at this going slightly further back in time, but I'm looking at the moment at Jurassic to present in my most recent work, and I haven't gone any further back in time than that. I think it would be very difficult to do this kind of work back in the Archean using the same relationship between lanthanum over samarium and temperature as I show in my talk, because in the Archean it was much hotter, and so you'd expect melt fractions to be larger, and incompatible ratios like lanthanum over samarium, if you have too much melting, become insensitive to melt fraction because they become equal to what was in the source originally. So you would if you were to do it, you would probably need to find a less sensitive trace element trigger to use that would work at higher melt fractions. But yeah, as I say, I think it would be difficult, but maybe it would be interesting to look at areas that you have volcanism versus areas that you don't. But I don't know how well we know whether the volcanism was intraplate or generated by other processes. I'm not an early Archean geologist, I'm afraid.
Okay, next question, please. Actually, I have a quick question for the clarification. So my interpretation here that when you refer to intraplate volcanism, you mean the volcanism as long as they are not occur at the plate boundaries.
Yeah, although there are areas in this where there obviously are at plate boundaries. Essentially, what I mean, I have a way of filtering the database to be only places that are away from plate boundaries. So I can look at strictly intraplate only, but really I just wanted volcanism that wasn't generated by plate tectonic processes. That's really what I was interested in. So somewhere like Iceland is generated by hotspot volcanism, so it's different enough to classic mid-ocean ridge volcanism to be included within the database. The same with areas like Mexico or Turkey, or even Eastern China, where you had subduction and then slab rollback or slab tearing, getting rid of the slab, and then you have intraplate style volcanism occurring in that area after the subduction has finished. And again, I'm calling that intraplate, but obviously it includes the water and the tectonic processes that happened previously.
Okay. Okay, here's another question from Chantal. Is there any other proxy expected for other than the LASM ratio in your research that you have used?
Yeah, so in the later part of my talk, I was looking at mid-ocean ridges, and at mid-ocean ridges you can't use lanthanum over samarium because melt fractions are too high. So instead, I used these other ratios. So I looked at samarium plus gadolinium over titanium. But again, you can see that that's not particularly sensitive to changes in temperature. There is a correlation you can see, but it's not a large one. There's not a large variation there. And then the other one is sodium concentration, but it would be difficult to use sodium concentration to look at stuff back in time because it's sensitive to changes in metamorphism or weathering, that sort of stuff. So I think you would want to stick to elements that don't move during metamorphism or weathering. Because in the Archean, obviously, you'll have had lots of those processes happen to those rocks since then.
Okay. Okay, actually, there's another following question. Is the can the LA-YB ratio be used in your research?
Yeah, it can, and it gives just as good a correlation coefficient, but I wanted to try and isolate the effect of temperature from the effect of lithospheric thickness, and so lanthanum over ytterbium is used commonly, but ytterbium is very sensitive to the depth that melting occurs at. And so I wanted to try and, disentangle these two processes. So instead of using lanthanum over ytterbium, I used lanthanum over samarium because samarium is less affected by the presence of garnet than ytterbium is. But yes, it can be used, and it gives a good correlation.
Here's a second question from Yifeng Chen from Zhejiang University. So it's a temperature and a melt fraction estimate from this work that's available.
Yeah, it's there's a table in the supplementary materials in the paper, and that has all the information for every province within the data set.
Okay, I think that's all about today's webinar. Thank you very much again, Patrick, for giving the great talk, and thanks everyone for your participation. And next week, we are going to have the very last talk in our webinar in the year 2021. So welcome to join our webinar next week. So have a good week, everyone, and thank you very much again, Patrick.
Yeah, thanks very much for having me. Yeah, it was great, and I'll see you at AGU if anyone's going to AGU.
I think, yeah, okay. I think people will attend online. Some of them.
Yeah, I'm going online as well. But
okay, great. Okay, bye bye.
Thanks very much. Bye.